Good afternoon, everybody. Hope you had a lot of coffees so that you can listen to the most exciting topic of this show, security. So my name is Nama Bak. I'm with NXP Semiconductors doing business development on an IoT security. For the people who does not know who is NXP, NXP is a $13 billion company. We are one of the biggest supplier of semiconductor in the world. Microcontroller, microprocessors, analog connectivity. Most of devices you see here across the show, cars, EV charger, most likely NXP is inside. Okay. The scope of today's presentation, it's really security. We're going to talk about the challenges of securing EV charging. So what are those threats? What are the regulatory requirements in the space of EV charging? And so how we can address those threats as we go with solution leveraging hardware and software. And then I'm going to show you at the end a little bit of what NXP really make in this area. Prepare your question and feel free to ask them at the end. All right, so there are two key factors today that should get you concerned in the space of EV charging in terms of cybersecurity. Number one is the attack vector, attack surface. There has been 14 million EV cars sold last year, okay? That's a lot, and this is 34.5% more than the year before. And as we know, by 2030, some of the countries in Europe, they're gonna be even more, okay? This means a lot of EV charger, but this means as well high stake for hackers. High stake for hackers because there is user information, including payment information. There is as well impact on the economy in terms of charging infrastructure. So if someone can get to those 14 million, he can really make bad thing, okay? The second factor is definitely the complexity of the EV charging system. There is the chargers, there is the vehicle, there is the grid. There are a lot of entity there, which make it really very complex to secure from cybersecurity perspective. Someone can get access to the charger, now he can get access to the grid. If the charger is super secure, but the vehicle is not secure, then there is an issue. So those two factors, meaning the number of units now in the field and the complexity of the ecosystem, making it now very complex and very hard, and it's a critical issue to consider as we go, meaning security. So what we need to do, we need to deal with it. And to deal with it, you need to understand what are those threats, okay? So if you look to the ecosystem, like from the vehicle to the charger, there is the vehicle in the left, as you see here, the charger in the middle, and then whatever energy source on the right. Threat, they come from everywhere. But today we're gonna mainly focus on what is in the middle, the EV charger. There are a lot of paper out there that explain real threat that happen. Actually, most of the EV charger that has been deployed as of now, there are vulnerability, okay? And this is not just my statistic. This is really backed up by a real analysis. And I'm gonna just give an example of some threat. Supply chain. When you are manufacturing an EV charger, you're gonna buy components from CM, potentially in China, okay? You're gonna buy components that they have a hardware inside, like a processor, operating system, and you're gonna use those for metrology, for cloud connection, things like that. You have to verify what is inside. Otherwise, someone can inject a malicious code inside, like a backdoor, that he can use simply to block the EVSE when it is in the field, or simply to steal the user data. And this is something that happened really between Ukraine and Russia. There has a Russian company that bought some component from a Ukrainian company before the war. And then after the war, definitely the Ukrainian company remotely get access to that EVSE in the street and start to display some political message. This is a fact. So this is not just a dream or a risk. This is something that really happened. And same thing can happen for every charger here. So you need to make sure that whatever component is inside your EV charger, you verify its integrity, its origin, and things like that. The second hack I would like to highlight, which is real, we see a lot of nice EV charger across the show here. It's very easy to duplicate one of those from look and feel. It's a box. Nothing prevents me to build the same box and put it inside the street. Even inside, there is everything, it's a fake. including malicious code, malicious hardware. And then me as a driver, as a user, when I'm going to come with my car, there is no way for me to verify if this is a real box or false box. And one of the attacks that has been described is the driver with his car, he stopped close to a fake EVSE. He's going to plug his car. That fake EVSE is going to get the data of the user, the identity of the car, and send it to another malicious person who is really in front of a real EVSE, and then spoof the energy for free. Okay? So that's, again, it's not just a risk or a dream, it's something that really happened. Okay? So there are a lot of threats, and we can talk about it for hours, but they are real, and there is a reference there that you can look to. The good news is regulations start to look to this across Europe, even Asia, and the US. And there are standard now regulation that they specify requirements who address those threats. We're going to talk about 8 of them. Number 1 is the EU battery passport. This may not be applicable directly to the EVSE, but if an EVSE has a battery that produces more than 2 kilowatts, it's going to need by 2027, February 2027, to have what we call a battery passport. The battery passport is a QR code that allows the user, when it scans it, to get static data, so the battery origin, the chemical behind, who is the manufacturer, and then dynamic data, state of charge, state of health. And this is an obligation. If you don't have that, you cannot sell battery anymore in Europe. Okay? And this is definitely increasing security versus supply chain attack. So as of now, it's easy to put copy of battery with no quality. With this, it's going to be harder. The second one is OCPP. I think everybody knows OCPP. But OCPP, what is good about it is specifying a lot of features about cloud connection. The way the EVSE connect to the operators should use methyl authentication. OTA data as well is mandated, and many of those features that make it hard to execute the threat that I showed before. ISO 15118, that's for interoperability between the vehicle and the charger. There is the -2, which is already good. There is some authentication of the car. It's leveraging PKI, but definitely the -20 is bringing better security, because without methyl authentication, the attack I described before, it become real. Meaning a user can use a fake EVSE without knowing he's using really a fake EVSE. And the -20, by the way, is introducing new cryptography, including elliptic curve 521, where the current -2, it's only elliptic curve 256. And then ICNC, this is for Germany, calibration law. So if you are doing an EVSE and you are generating measurement, definitely you need to use what we call a root of trust to generate and create those measurements, leveraging a private key which is stored securely inside the device, including the measurement unit, the measurement themselves, and the ID of the EVSE. This is a way to prove the transaction that the user was doing. And then there are other standard and regulation, mainly for residential EV charging. For the people who does not know, CSA Matter. Matter is the new standard for smart home. So have been convented by big company, and then XP is in the board. And the Matter, 70% of the spec is mainly security. It describes the crypto primitive that an EVSE need to use within the home. It describes the protocols, how the EVSE going to be communicating with the cloud, how it's communicates within the home, and things like that. So this is definitely increasing way better the security requirements compared to what we have today. US Cyber Trust Mark. This is something that the Biden government announced last year, if I'm not mistaken. It's a voluntary program, but it gives incentive to the OEM who are putting security. And you are, as a EVSE manufacturer, you can apply to this program. And if you provide all the evidence about the requirements, you're going to get a stamp, which you can put on your device. And so me as a user at home, when I'm buying an EVSE, most likely I'm going to use the one that has the US Cyber Trust Mark stamp versus the one that does not have it. Because I am sure there is a security implementation that has been verified inside. Okay? And it's not a dummy EVSE with no security. So this is a voluntary program as of now, but we expect it to be mandatory as we go in the future. CRA. This is, however, mandatory. Everything that comes from Europe usually is mandatory. So Cyber Resilience Act. It's being voted now, but we expect it to be voted end of this year. And it's identifying a set of security requirements from process and product perspective. For OEM, building devices does not matter the type of device. Charger, thermostat, whatever. If you don't follow those requirements, you will not be able to get the CE mark. And so meaning you cannot sell in Europe anymore. If it's entering law by end of this year, by 2027, it's going to become a mandate. So we have 3 years to comply. And we're going to see what is really inside. And PQC, this is just as a reminder, cryptography is evolving, and post-quantum crypto is coming as well with the quantum computer. And we expect that by 2030, quantum computer going to be real. And so there is a whole migration that needs to happen by that time of the current crypto that they are specified in the current standard to a new crypto suite that can resist against quantum threat. So, a lot of standard, a lot of good intention. Now the question you may ask, what is really inside? The good news is there is a baseline of requirements across all those standards. 80% of the requirements, they are the same. Does not matter, we are talking about CRA, we are talking about the US Cyber Trust mark. They share about 80% of the requirements. So if you implement one, it's easily that you can get the other one. And there are 3 layers. Number 1 is the root of trust. The hardware root of trust that your EVSC gonna use. Where you're gonna store your key that you use for the ISO 15118. The root of trust to store as well your key that allow your EVSC to communicate to the cloud. Protection against physical attacks. So even if someone has access to my EVSC in the street, he should not be able to dump the firmware or change the firmware running there. So this is the hardware root of trust. The second layer is the platform security. This is where your hardware and operating system gonna run for meteorology, for metering, for cloud connection. And there you need to have things like secure debug, secure updates, secure boot, to make sure that the software running within your platform, it's really the software you have provided. And when you make an over-the-air update, you are sure that only your OT update can be executed and not a malicious code. And then the third layer is what we call security processes. Processes meaning the way you produce your code. Is it really secure by design? Are you making some vulnerability assessment? Do you produce documentation? Do you do like a good user authentication? So all things that come on top of the hardware and the operating system. If you achieve those 3 layers, you're going to be able to achieve or to meet compliance to those standards, and then definitely address the rising threat. So what do you need? You need definitely a hardware foundation. There is no security in the EVSC without hardware. Whatever software implementation you have today, it's still software. You can use obfuscation, you can use white boxing, but there is a limitation. I can reverse engineer a code. I don't need to be an expert. Just a student can get the code, start to look to it, use some tools to get access to the key. So there is a limitation definitely to software implementation. This is why hardware is very critical to implement security, because the hardware by design is complex. While someone can reverse engineer code and look to it, it's not obvious for someone to understand the design of a chip. Where is the ROM? Where is the RAM? Where is the CPU? How the key they are stored? That require more expertise. And now we are rising the bar from something very simple to hack to something very hard to hack. So hardware is definitely critical as a baseline foundation to meet those security requirements. If you have a secure hardware that allow you to do key storage, secure boots, secure debug, all the requirements we have seen, then you're going to save money. You're going to save time. You buy a chip that has everything you need. You put your software on top of it. Definitely, there is about 50% of the requirement they're going to be met already by the hardware, and you're going to just focus on the remaining 50 or 30%, which is about your app, the way you produce your code, the way you check vulnerability on your cloud, and things like that. And then you take the evidence, oh shit. So, sorry, I did not have coffee. So you take those evidence, you apply to CRA, to the US Cyber Trust Mark, and then you get your stamp. You are saving time. Instead of spending a process of 6 to 12 months, now you are just doing 1 month. You are saving money because those resources that you are putting on this process, you can put them in functional things that really bring money to you. And then definitely long-term security. Because it's leveraging hardware implementation, most likely your security going to resist against attack for the long time, meaning more than 5 years. This is the reason why hardware foundation is important. Now you should wonder which hardware I need to use, or you are already using hardware and you're thinking, it's really secure? So there are 3 architectures that exist in the market today. At NXP or outside NXP, this is really about the market. You will find processor with what we call like basic security hardening, like microcontroller, microprocessor leveraging mainly trust zone as a way to isolate secure process, and they have secure boots. This is the one in the left, and you see here some of the NXP processor example. And then you have in the middle what we call secure enclave. Those are new type of security architecture. So inside the processor, you're going to have the trust zone, but you're going to have as well what we call a secure enclave, which is a fully isolated like core. It has its own ROM, CPU, dedicated to security function. It's fully isolated from your app. So when you store key, your key, they are never accessible to that Linux or RTOS without authentication. If someone gets access physically to that chip that has a secure enclave, just by dumping the memory or by reverse engineering the software, he will not be able to access the key. He's going to need to invest a lot. And that's making it hard. And here you see some example of the NXP processor that we have. And then on the right, it's what we call secure elements. Secure element, you can look to them as a small chip, the same that you have inside a passport or a phone. So when you pay with your phone today, it's a secure element that secures the transaction. Maybe you will never wonder, but there is a secure element most likely inside your phone. It's exactly the same chip that we have token and qualified for IoT, and you can add it to any processor from an XP or from outside an XP. And it will allow you to store the key. You have internal flash. It will allow you to do crypto and a lot of those security mechanisms that we have been seen before. So you have 3 categories, and you need to choose the best category that fits your requirements. As we go, we're going to focus on the one that they are mainly on the right. So to give you more color about the secure enclave, as I said, it's really an integrated IP within the processor. It's independent from the operating system you are running. You are using Linux or RTOS. The secure enclave work with it. There is no royalty to pay usually with the secure enclave architecture. And to access to the secure enclave, usually we provide what we call a middleware. So we don't need to write code inside. It's already written usually by the company like an XP certified. And you have just a C code-based library pre-integrated within OpenSSL, PKSS 11 for the people who knows, to generate me a key pair, sign, encrypt. That's it. So you are mainly focusing on your functional code instead of focusing on the crypto. Everything is provided by the secure enclave. And the secure enclave usually work with other components within the processors, like accelerator for AES. When you are doing TLS, you want that session to be very fast. So it's not really replacing the existing IP, but mainly enhancing the existing IP. And it does not have a cost either. It's already integrated within the processor. So whatever processor you choose, you need to have a way to do updates. We believe at NXP that there is no security without updates. Whatever you put today in the software and the hardware, it's going to be outdated in a couple of years. So you need to have a way to do over-the-air update, not physical update. Physical update work for a startup that they have 1,000 of FVSC, but it does not work at scale if you have million. Otherwise, the cost can increase. So definitely you have a way, you need to have a way to do remote update. Remote update of what? Of the key. That key that you use for ISO 15118 or to connect through OCPP to the charger operator. It's leveraging maybe a certificate that is valid for 2 years. You need to have an expiration date which is limited in time. And then you do certificate rotation and key rotation. Because the more the key is used, the more the risk is high. Update of the software. That Linux Yocto that you are using, it has vulnerability definitely, and there are vulnerability every month. And you need to have a way to patch it. Even the open source thing that you are maintaining, definitely you need to have a way to patch it. And patch it remotely. And in XP, we do have something called EdgeLock to Go that allow you to implement this strategy with our processor if you are using an XP processor. All right, so we talked about the architecture with the secure enclave. With the secure elements, you can use a securement. As I said, it's like a passport for your EVSE. The securement by design protect against the highest type of attack, meaning even if you have the chip between hand, I need to invest up to $2 million to get to the key to one chip. That's the protection profile. And it's not just a claim. It's backed up by a real third-party certification. That's the level of security if it is needed for your EVSE. For example, if you are selling this to a government agency to be installed inside a building, most likely they're going to ask you for such level of security. And you can use the securement to achieve that. The SE, it has internal secure flash, tamper resistance. It provides a software library that allows you to do sign-in using ECC, RSA, AES, and all the type of crypto primitive. And it's independent from the processor. So you can attach it to any processor. Even a Cortex M0 Plus can work with the MCU, all the way to Cortex A35 and 55. All right, so if you use now a hardware foundation with security, what you're going to achieve? Well, compared to that first slide, a lot. First of all, secure manufacturing. Because the processor is going to come with pre-provisioned key, your key, then you don't need to rely on CM to do this. And so you are reducing the risk of injection of malicious code by those CM. So the chip is locked. You can use those keys to onboard your device to the cloud and to communicate with the vehicle. So secure manufacturing, thanks to that pre-injection of the key. Protection against physical tampering. Because the processor has capability to detect attack. So if someone opened that EVSE box, there is a tamper pin that's going to be triggered, and it can send an event to the secure enclave, and then the secure enclave is going to reset the CPU of the core. So now you are making it hard for the attacker really to change your firmware. So that's what we call about tamper resistance. Definitely compliance to ISO 15118 plug and charge. By default, most of our processors, they can achieve this. And we have a reference design that I'm going to show you in the coming slide that allow you to implement ISO 15118, leveraging the NXP security. Secure OTA updates. That's something you can achieve. The secure enclave is programmable. So if there is an issue with the crypto, or if there is a new functionality you need to push, you can do it directly through NXP. Our secure enclave is programmable. You can push new key length. You can push new like application if it is needed, or patch availability. That's definitely something that you're going to achieve with a hardware foundation. And measurement signing. This is mainly to achieve the ICNC certification. ICNC, as you know, it requires you to have a root of trust to sign the measurements. Since the secure enclave and the securement, they have capability to do it, you will be able to achieve it easily. All right, so to summarize, to address those threats that we have seen and to comply with the regulation requirements, there are 4 steps. Number 1, select carefully your software and hardware foundation. Everybody can claim inside the data sheet that they are secure. But the only way for you to verify that hardware is secure is through a third-party certification. Ask, are you FIPS certified if you are going after America market? Are you Common Criteria certified if you are going after Europe market? That's going to help you to assess the security of the processor you are selecting and have evidence later that you can use to have your own certification. So software and hardware foundation certified and proven. Once you select that, then pay attention about where you are making the provisioning. The provisioning of your key, the provisioning of the software. Use trusted facilities. A lot of EVSE manufacturers, they may choose the easy path, which is get to a CM maybe somewhere in the world. It's very cheap, it's easy. But then how you are sure that they really provisioned your firmware? How you are sure that they did not inject some malicious code? This is why this is very critical that you choose your trusted facilities, or you use a tool like what we do at NXP to provision your key securely, and you make sure that it's independent from the CM and ODM level. Once you do this, then number 3, you can use the evidence that the hardware provide and the capability of the secure manufacturing to certify your device. CRA for Europe, Trustmark in the US, ISO 15118, OCPP, and all of those zoo of standard. And then maintain your security. Remember, there is no security without update. So whatever you're going to select there in terms of hardware or software, make sure you have a strategy to do OTA update. All right, so just to finish, at NXP, definitely we do have multiple processor architecture with security levels different from one to the other one. We do have processors that they have basic security hardening, leveraging maybe trust zone. We do have processors that they have a secure enclave, and we are shipping a lot of those, like Cortex-A for EV charging, like ICNC24. We do have as well Cortex-M33 for smaller like EVSC, where they have secure enclave directly. And then we do have secure elements. Remember that passport for your EVSC, it's as well possible with NXP. We do have something like SEO50 family. You can check it out. nxp.com/SEO50 that provide you that passport for your EVSC. You can work with us, definitely. Why? You will have the flexibility of choosing the right security hardware foundation you need, from basic security hardening to the highest level. Definitely you need to understand which hardware you need based on the cost constraint you have. We pre-certify our chip. We invest millions of dollars per year to pre-certify our chip, things like FIPS, PSA, CSIP, Common Criteria, so that you can use this evidence to do your own certification. And when we make a claim about security, we don't ask you to trust NXP. We ask you to trust those third-party evaluation. That's going to help you as well to shorten your time to market. And the last thing, you may have the best hardware in the world, but if you don't have software to use it, it's useless. You can get the best hardware in the world, but if you need to spend 12 months to just do key storage, it's useless. This is why we invest a lot on software. When you get the hardware, you're going to get a software library that allow you to do everything I was mentioning before in terms of crypto, storing key, doing signature, secure boots, and so allowing you to save that time of engineering and security enablement. So that's one of the benefits at NXP. And you can find more at nxp.com/security. And then my last slide, if you are interested to do some evaluation, we launched in June what we call Easy EVSC. It's our reference platform for EVSC. It have everything inside, like a Linux platform, plus a microprocessor, microcontroller for metrology and Wi-Fi, and it has as well HMI for screen, and it have security software inside, as well ISO 15118 stack. So when you start with this, you can experiment everything I was explaining before in terms of security, hardware root of trust, platform security, and processes compliance. So check it out, and if you have any question, I'm here to answer. Thank you so much.
Thank you, Nama. Are there any questions?
Thank you. Thank you for the great talk. When will it be possible to support the algorithms for -20?
Can you repeat? Can you repeat, please?
When will it be possible to support the algorithms P521 and ED448 for -20 plug and charge?
For on an XP processor? Okay. So the question is, when an XP gonna support the -20 new algorithm, ECC521? The answer is already supported. Okay. We support the primary algorithm, meaning ECC521 inside our securement, SEO50, for example, and inside our enclave, like ICNC93. For the backup algorithm, ED448, that's something we are planning end of this year. But they are only backup algorithms.